Okay, so welcome everyone. We are very happy to have Mykola Dedushenko today from Simon Center, who is going to tell us about stable envelopes and Janus and QFT home for some geometric constructions.
All right. Thanks a lot for inviting and for introducing. Now let me start sharing. Okay. So this talk will be about the physical realization of certain mathematical constructions, and namely those that originate from papers of Maulik, Okounkov, Aganagic-Okounkov, Okounkov, Smirnov, etc. On the one hand, and on the other hand, there were earlier works by Nakajima and Varanola where they realized certain actions of Yangians or quantum loop or elliptic groups in the cohomology theories of quiver varieties. So, well, elliptic, of course, it appeared later and sort of follows from the construction of papers in the first line. But in this talk, I will mostly talk about the physics part about the physics construction, and I won't review too much the mathematical construction, in particular stable envelopes. I will assume that since there are experts in the audience, that people are mostly familiar with it. So the constructions that appear in these mathematical papers, they look very physical, so to speak. And in particular, maps, for example, maps between cohomology theories, equivariant cohomology theories, that are defined by certain correspondences, they remind interfaces between quantum field theories. And in fact, then these structures, they can be viewed as part of, or should be viewed as part of the Bethe gauge correspondence due to N.Nekrasov and Shadashvili. So yeah, and then when I say the interfaces between quantum field theorists, I mean quantum field theorists, say QFT and QFT1, whose, as we'll see, Higgs branches are the corresponding varieties X1 and X2. So the main idea will be to introduce certain supersymmetric interfaces between supersymmetric quantum field theories that would induce linear maps between the spaces of SUSY ground states. And those linear maps would lead to the structures that we're after. So, for example, and of course, there's a multiplication on the interfaces essentially for free, because you can imagine that you have, say, QFT1 here, QFT2 here, QFT3 here, and then you collide interfaces and you get a new interface. So we will think of them, well, we will mostly work, essentially work in the Euclidean field theory, but you can think of the direction normal to the interface as time, so that the interface is represented as a operator acting on the Hilbert space. So they would be like space-like if we decided to rotate back to Minkowski's signature. And the playground will be theories with 8 supercharges in 1, 2, and 3 dimensions. So in 1, these are n=8 theories on a line, or they will be broken, the SUSY will be slightly broken to n=4. And this is related to cohomological constructions. Or in 2D, those are 4,4 theories on a circle times a line. And 3D are n=4 theories on elliptic curve times a line. So we'll identify supersymmetric Janus interfaces that turn out to be building blocks of this, the whole structures. And spoiler alert, they will be related to stable envelopes. Then one can look at the matrix elements, and the main slogans for this business is that stable envelopes, they correspond to phase transitions in these theories, whereas R matrices that one can then construct from them correspond to wall crossing. So yeah, so this is like a very broad motivation. So let me start with some more concrete things. Well, first of all, let me remind you that, of course, so we will deal with 3D n equals 4. I will mostly talk about 3 dimensions, and everything else follows by dimensional reduction. And we'll work with 3D n equals 4 theories, thought of as, or viewed as n equals 2 theories. So n equals 2 gauge linear sigma model is defined by the data of course, gauge group, and complex representation R, superpotential W, which is invariant function on R. And then there are real masses MR and real Fi parameters, zeta R. Now we focus on n equals 4 theories, whose matter is valid in some quaternionic representation, which will take like this, so theories of cotangent type, where R is some complex representation of your gauge group. And so viewed as an n equals 2 theory, it has chiral multiplets Q, Q tilde, and Phi, where Q is in this complex representation, Q tilde is in the dual, Phi in the adjoint, and Phi will also be denoted sometimes as sigma C. And then the superpotential is the n equals 4 superpotential is like this, plus the term that might have we might have a term with complex masses, where MC is a diagonal matrix, and there might be also a term with complex Fi parameters. The n equals 4 R symmetry, we will in the n equals 4 R symmetry, we'll only focus on the maximal torus, which is U1 Higgs times U1 Coulomb, and the diagonal U1 is identified as the n equals 2 R symmetry, while the, let's call it the antidiagonal U1 is this special flavor symmetry U1 H bar that's present in the, that's flavor symmetry from the n equals 2 point of view, but is part of the R symmetry group from the n equals 4 point of view. So the full n equals 2 flavor symmetry is the n equals 4 flavor symmetry times this additional U1. Now, masses and flat connections for this additional U1, it's called softly break n equals 4 down to n equals 2. And then, so we will allow such soft breaking. But we always want to preserve the U1 H bar symmetry. Now we'll, as I said, we'll look at 3D, 2D, and 1D theories. 3D theories on the elliptic curve times line, 2D theories on the circle times line, and 1D theories just on the line.
Question, why do you want to look at, say, 3D theory on circle times R2?
You could do that. It will be some different problem. Like, or
but so instead of envelope, you'll get what? Like, is it easy to say? You're going to have some different realization of this algebra, right? But
well, you will. Okay, so you can think of that as a degeneration of your elliptic curve. You just take one of the cycles very large.
So is it going to be trigonometric limit of the stable elliptic envelope?
Yeah, there will be a. It would be trigonometric limit.
I see. Okay, that's interesting. Okay.
So, and then the notation we'll use as the x H is the Higgs branch of this theory, XC is the Coulomb branch, of the 3D Coulomb branch, because of course it depends on dimension. And we'll think of quiver theories, so XH is the quiver variety. And we'll work equivariantly with respect to the maximal torus of this flavor group, the N=2 flavor group. And then interested in equivariant cohomology, K-theory, or elliptic cohomology of the Higgs branch. And as I said, we must preserve H bar, U1 H bar. So in particular, complex masses that were present in the superpotential of complex of 5 parameters, we're not allowed to turn them on. But we can have real masses in that are valued in the Lie algebra of the maximal torus of the flavor symmetry, or real Fi parameters. Now here I wrote on an N=4 flavor symmetry. In principle, you could also have flavor masses for this additional U1 H bar, but as I will explain soon, it's not useful to turn them on. Turning them on introduces certain non-universality in the construction. And this spaces of real masses and real Fi parameters, they have certain chambers. At the walls of those chambers, for example, in the space of real masses, at the walls, some of the fields in your theory become massless, and so like you get some non-compactness, and that's why when you cross those walls, interesting things might happen. So in these theories, there are several supercharges that lead to several interesting constructions. So again, we consider theory on E tau across R, where R will be parameterized by Y, Euclidean time. And then to E tau, we associate H of E tau, the Hilbert space. And let's pick some supercharged Q. In our SUSY algebra, it acts both on the Hilbert space and on observables in your theory, local or extended observables. And then the classic path to interesting mathematical constructions is path to Q cohomology, possibly equivariant if Q doesn't square to 0. And look what happens there. Now, the standard argument is that with respect to Hermitian inner product on this Hilbert space, which of course should be defined with R when R is given Minkowskian signature, but then that structure passes over to Euclidean. So with respect to Hermitian inner product on this Hilbert space, there's also Q dagger. And then, of course, when you look at the Q cohomology, when Q acts in the Hilbert space, you can identify it with a kernel of Q, anti-commutator of Q and Q dagger. So just like in Hodge theory. And often it happens that Q dagger is the Hamiltonian, and then this kernel is just the SUSY ground states. So the Q cohomology of states are just the vacua. And Q close observables lead to linear operators on the space of vacua. Now, there are basically 3 interesting supercharges in 3D N=2. So one is QA, the 3D uplift of the 2D A model supercharge. So that just in 2D, that's just the Gromov-Witten theory. And it lifts to the A branes lift to 1,1 boundary conditions in 3 dimensions. And that's this supercharge is actually squares to rotation of one of the circles, plus some gauge and flavor transformations. And this, looking at the cohomology of this supercharge, is what's sometimes referred to as a 3D A twist. For example, it has appeared in a lot of physics literature. And in particular, an interesting partition function in this case is this cigar times S1 with And then you twist cigars, you go around S1, which leads to a K-theoretic count of quasi-maps, which, of course, is discussed, for example, in Okounkov, in Aganagic-Okounkov, and many other papers. And then, in the 2D analog is the cohomological count of quasi-maps. Now, another interesting supercharge is QB, which is the 3D uplift of the B model supercharge. And this one, in this case, B branes live to 0,2 boundary conditions, and the corresponding 3D supercharge is sometimes called the 3D holomorphic topological twist. I mean, the passing to the cohomology of the supercharge. And for example, last year, there was a paper by Costello di Moftagaioto looking at the vertex algebras that are structures in the cohomology of, when you look at the cohomology of observables, local operators in the Q cohomology. And finally, another interesting supercharge, which is the 3D uplift of the, so to speak, omega deformation supercharge in 2D, which is common both to A and B models. It can be, this, we'll call it just Q, can be identified either as QA plus QA dagger or QB plus QB dagger. And this is the supercharge that's the common Q preserved both by A and B branes. And from 3D point of view, it's also the supercharge that belongs to a 3D n equals 1 algebra. Now, again, I already said many times that we consider theory on E tau across R, and then this supercharge Q squares to the anti-holomorphic translation along the E tau direction. One can check that it's still true that the Q cohomology on the Hilbert space for this supercharge is just the SUSY vacuum on E tau, and since Q squares to this translation along the elliptic curve, the Q cohomology of operators will contain just certain interfaces wrapped on E tau. Right, they cannot be local operators lines because they must be invariant under this translation. And later we'll also observe certain relation between Q and QA. Well, not relation, like there will be certain device that connects them. So let's look slightly in slightly more details at Q. The BPS equation. Yeah.
When you say the ground states can be identified with the Q cohomology, that would not be true if you tried to if you looked at QA or QB, or would it?
Oh, it would still be true. Yeah.
So you'll have a variety of different cohomology theories which will look non-isomorphic but will end up giving the same answer, or will they be trivially isomorphic, just related by some R symmetry action?
Well, as vector spaces, they are just isomorphic, but then the structure of local operators that act on those vector spaces, those are different.
So okay, so you'll can you get some non-trivial predictions by considering this vector space in those three different ways?
Perhaps. Yeah, so essentially when you look, for example, at that vector space through the lens of QA, you think of it as a K-theory of your targets, and then there are actions of line operators on it. But for example, on that vertex function, they act with certain difference operators. But then when you look at it through QB, for example, then I guess there's action of vertex algebra. And when you look at as a cohomology of Q, then there are these interfaces like surface operators acting on it. So yeah, there might be more there to explore. Like I will tell you about one particular aspect. Well, not exactly what you're asking, but this certain connection between Q and QA.
Okay, thanks.
So the BPS equations for Q, and so here E tau is coordinatized by Z and R by Y, as I already said before, just reminding you. So the path integral localizes on supersymmetric configurations determined by the BPS equations. And the most important ones of them are the following. So one is that dW is 0, which in particular leads to the complex moment map constraint. Then there's this equation that dy plus sigma r plus mr on any chiral multiplet is 0. And another equation that dy on your real scalar is real moment map plus sigma c bar, where sigma c is the same thing as phi, what I called phi before, the capital Phi. So these equations, in particular, these two equations here, give you the gradient flow on the representation space times 3 copies of Lie algebra mod G. And this can be thought as a gradient flow for the following Morse function. So here's the part for gauge symmetry, gauge group action on the hypermultiplets, also on this additional chiral multiplet in the adjoint, and then there's a flavor group action. Right? And then there are additional equations that follow from equivariance. That is from equations like this, such as the dz bar phi equals 0. They're somewhat less important and taken care of later. So we neither have, with these equations, we neither have stability condition nor a real moment map. Instead, there's a gradient flow on the surface of a complex moment map constraint.
So far, in none of this, you're saying, is it important to actually take the torus to be a torus as opposed to decompactified into S1 times R? Could you try to keep that? I think that's the really, really the more interesting thing to do, I think, because this story should be a story about boundary conditions of the 3D theory. That's a natural lift of the boundary conditions of the 2D theory, which of course you can think of as correspondences as well, as one usually does. But I think you want to keep that torus as non-compact as possible for as long as possible. And you can, right? So far we could just keep going with it, right?
Well,
it's interesting because I think what you really want, I mean, of course, what you're doing is very interesting as well, but you want the categorification of the stable envelopes to understand that the whole thing is coming up as traces of something, which is naturally is.
Sorry, I didn't hear one of the words you said.
You want to study, you want to, this is really a story about boundary conditions, right? Or correspondences, but I think you want to decompactify the torus. If you decompactify it, so you think of it as, okay, let's go back down to 2 dimensions, right? Then instead of studying the 2D theory on S1 times Y times your line Y, you would study the category of its boundary conditions, which we understand well, and this would lift you up to boundary conditions in the 3D theory, right? Your finding such Morse flows would be, particular solutions to such Morse flows would be particular solutions.
Well,
I'm not saying that. Okay, anyway.
sure. I mean, there would be a certain degeneration limit of what I'm talking about here. If
It's
like,
not a degeneration. It's not. It's a different question, right? As it's a different question. You want to. There is a bigger set of questions out of which this should come by taking traces, right? Namely studying boundary conditions in the 3D theory on a circle, where it's almost like boundary conditions in a 2D theory with this actual hidden circle in story. So
yeah,
but keep going.
Yeah, sure. Well, first of all, I want to really think about interfaces. Of course, people say interfaces like a boundary condition in the folded theory, but that's kind of tautology. So the real I'm talking about interfaces, and for me here I'm really interested in say the space of vacua on the torus, and then like matrix elements of these interfaces between different vacua, and that's something that would be a bit, I guess,
where I would take you would be towards categorification of those structures, which is naturally in your story. I'm just saying, I think you want to think about that torus as non-compact for as long as possible until you actually have to compactify to ask the specific questions that you'll be addressing right now. But there's this other questions, which I mean, the technology you're building seems equipped to take care of them for a while. Maybe actually all the way.
Okay.
I actually suspect all the way.
Yeah, we'll see.
In this condition 2 for the BPS equations, is phi there the phi from up above, the adjoint chiral multiplet?
It's any chiral multiplet, including adjoint one.
I thought you said we were on the Higgs branch, and so phi should vanish.
Well, I didn't say we're on the Higgs branch. Also, I said that here, as you see, so these are BPS equations. That's just something you get from SUSY. You don't specify, like, they dictate you where you are. You don't tell them whether you're on the Higgs branch. And in particular here, we don't have stability condition or mu r equals 0. So we're really not exactly on the Higgs branch. We have gradient flow on this space. But then, for example, if you don't turn on masses so that you really can have Higgs branch, then Higgs branch will be the endpoints of these gradient flows.
Okay, so there will be some solutions that will just correspond to phi being identically 0, and those will look like the normal Higgs branch, but that of the 3D theory. But then there will be other interesting solutions where phi has some dynamics. Is that the point?
Yes.
By dynamics, yes. I mean like non-trivial profile on the elliptic curve.
Yes.
I think his theory is massive, so there's no Higgs branch really. He just has isolated vacua where this wants to flow, right?
Well, masses can be 0. I mean, it's literally already written here. If masses vanish, then the fixed points of this flow have mu r equals 0 and sigma r equals 0, and you just land on the Higgs branch. So you just land on but if masses corresponding to some non-trivial subtorus are turned on, then the fixed points of this flow, it's not the whole Higgs branch, but just some fixed locus.
Okay, but in any case, shouldn't the adjoint chiral then vanish if we're on any point of the Higgs branch?
Sure, yes.
Okay. Identically, like it's not, there's no interesting profile on the elliptic curve.
Yes. And in fact, in this case, so the gradient flows, if we ignore how sigma r behaves, they look like orbits of your complexified gauge group. So indeed, those orbits that hit the fixed points, I think phi is just 0 there.
I think phi will vanish for him because he wants to make use of the symmetry that this anti-diagonal U1, which will make phi massive no matter what you do, no matter what the other masses do.
Yes, that's true. But here there are also some orbits where phi is non-zero, but those that hit the Higgs branch, their phi is necessarily 0. Okay, so okay, the Morse function the same as written above. Now, if I turn on, as I said, if I turn on masses, then the fixed points of this flow are not the whole Higgs branch, just some a fixed locus on the Higgs branch, and the gradient trajectories lie within GC times a orbits. So one could say that the Higgs branch image of this gradient flow, so if we additionally impose, say, stability and quotient by GC, they really look like orbits of your complex torus action on the Higgs branch, where the particular choice of torus is determined by masses. And then the fixed points are just the torus fixed points. Now, all the critical points of H of this Morse function, they have the same index, which is half the dimension of the space in which the flow happens. So you get half-dimensional attractors, and that's, I mean, roughly leads to the constructions of stable envelopes. Well, we will find that stable envelopes is really a map. I mean, that not like we find it was defined in such a way that it's a map from the vector space of SUSY vacua at non-zero mass to the vector space of SUSY vacua at 0 mass. And now we want to realize them by a supersymmetric interface that changes mass. So now let me move to the next part. Well, I would like to interpolate between different values of real mass while preserving Q. So I want something like this, to have a non-trivial profile of real mass, which is, say, 0 at minus infinity and something at plus infinity. And the of course, standard physical approach is to find a supersymmetric background that for background vector multiplets. So consider a vector multiplet gauging flavor symmetry. So in other words, we just turn on some fields like flavor connection or superpartners, but don't integrate over them in the path integral, and ask that fermions vanish and Q of fermions is 0. So here, just for concreteness, wrote this background flavor multiplet. The standard realization of the constant real mass is just to turn on this background sigma r, and all other fields are 0. But you can slightly generalize it, and in addition to sigma r, which would now make y dependent, we also turn on the background auxiliary field in this vector multiplet, I times the derivative of mr with respect to y. And it turns out that just this simple generalization, it preserves you 0, 2 SUSY, 2D 0, 2 SUSY, or even 2, 2, if we switch off that SUSY break-in parameter h bar. And again, for concreteness, here's the mass term in the Lagrangian. So your usual terms plus this additional term with derivative. Now one could ask how universal is this? Namely, what depends on the profile of mass? Well, like what happens if we slightly vary m of y? And in general, n equals 2 theory, the variation of the mass term is non-zero and not even q exact. So the details of this mass m of y are important. However, in the n equals 4 theory, it turns out so one can show that the variation of the mass term is q exact plus some expression with auxiliary fields, which vanishes under the correlators due to the specific form of the superpotential in n equals 4 theory. Well, as long as we keep mass fixed at infinity. So the precise shape of this profile doesn't matter. We just pick values at minus and plus infinity and interpolate them in some way, get a unique answer in the Q cohomology. In fact, only chambers of this mass matter in the space of masses. Where I remind you that the space, this the Lie algebra of the maximal torus of flavor group, it is divided into chambers by certain root hyperplanes, which is where those values of masses where some of your fields become massless. So physics provides us a unique up to q exact terms interface interpolating between these masses. And since the Q cohomology of states is the space of vacua, we get a map in the Q cohomology, which is just map from the space of vacua on the left to the space of vacua on the right with different values of mass. Additionally, one can also get analogous construction for Fi parameters, where you can vary a Fi parameter in a supersymmetric way. It's clear that such construction should exist because the Phi terms are just masses for topological symmetry, where just reminding you that if A is a U1 gauge field, then you can just take star F star of dA and say that it's a current for your topological symmetry because it's trivially conserved. And so one can also do the same thing for real Phi parameter and get a map that from the space of vacua at different values of the real Phi parameter. By varying parameters in this theory, so since we don't have more than two non-compact directions, and it really makes sense to talk about not about like branches of vacua, but rather about phases. And there's the Higgs phase corresponds to large Phi parameter and masses are 0. The Coulomb phase, of course, the opposite. We take large generic masses and the Phi parameters are 0. And then we can just take these interfaces and construct such a thing. Just take a product, which can be thought of as a phase interface between Higgs and Coulomb phases. And this part we thought of as a stable envelope for the Higgs branch, because that's where when you vary the mass. And as I sketched earlier, it can be understood in terms of the original theory via the BPS equations, which are gradient flows on the Higgs. So this object is sort of interesting in the Higgs phase. And then there's another mirror object, which is a stable envelope for the Coulomb branch, because the Phi parameters, they play the same role for the Coulomb branch as masses are for the Higgs branch. So they give you certain flows on the Coulomb branch. But if you want to get sort of this analogous description in terms of BPS equations, you would have to go to the mirror theory, because Lagrangian description is sort of asymmetric between Higgs and Coulomb. They're not described in the same way.
And you're prevented from varying both simultaneously?
I think you can vary both them simultaneously.
That shouldn't be right. You shouldn't be able to somehow.
Well,
envelopes
okay.
don't come from varying both for sure.
So here I put it in such a way, in such order that you never go through the region where both of them are 0. So perhaps that would be somewhat dangerous.
I thought the description roughly you get is that you get a stable envelope of the Higgs branch by picking a specific value vacuum for the Coulomb fields on the Coulomb, specific fixed point on the Coulomb branch. That's kind of the correspondence between them. So you should see that you should not be allowed to vary both.
You're saying so the stable envelope for when I get stable envelope, just for example, for the Higgs branch, I keep zeta r fixed.
No, you don't keep zeta. It's like so you certainly keep zeta fixed. You also keep fixed. Well,
okay.
It's correspondence between a vacuum, right, and a cycle on the Higgs branch, right. So this vacuum in particular picks a point on the Coulomb branch, a single point, because it's a vacuum.
That's a special case, right? In general, you can have a mixed branch, for example, and these constructions would still be defined. Perhaps they're more challenging to describe explicitly or mathematically, but yeah.
Okay, good. Yeah. So I see. So you're saying maybe there's something more.
Yeah.
And in these theories, you don't get sharp phase transitions, right, between the Higgs and the Coulomb, right? You can't, because you're basically in one dimensions. So there isn't a sharp division between the two. Anyhow, right?
Yes. But you can sort of change this profile, vary, and make it jump abruptly, and then you will have like a quantum quench setting. Like you have a wave function for this phase, then you suddenly change parameters, and it somehow distributes between vacua in the different phase.
Okay.
I think what Min is saying that there are only crossover traits. You cannot have a smooth, sharp phase transition, only like a large N or something like that.
Oh, so that's a comment or a question?
Yeah. So somehow it should be part of your story, I guess. It has to somehow be part of your story. Certainly, if you're in quantum mechanics, that you get kind of two phases which smoothly join together, and on one side it looks like a point, and on the other side it looks like a cycle. Your interface. But keep going.
Okay. So this whole business is really part of mathematical part of. So we study this Higgs and Coulomb phases and transitions between them, and that's really should be thought of as part of symplectic duality mathematically, as argued by Bullimore, Dimov, Toyota, Hilbert. So to study Higgs and Coulomb phases within the same theory. So now let us apply this. Just have illustrate, so to speak, these constructions. As I mentioned, there is this object that counts. That's defined in the case of A twist. The partition function on the cigar, or the vertex function, the K-theoretic count of quasimaps. where the cigar, it prepares you a certain state C, and then you take its overlap with a vacuum alpha. And in the A-twist, the relevant PPS equations are just this. So they tell you that you get vortices, and in the limit where E goes to infinity, you just get quasi-maps, which is so like a holomorphic maps, where you can have vortices at selected locations. But there exists another background that computes the same quantity. That's a cigar without a topological twist. That's usually people talk about the round hemisphere, which computes the half index. But there exists a deformation where you stretch into a cigar. It's the same thing that in 2D was done by Gomez and Lee, where they show that the sphere can be stretched into a cigar and you get A and anti-A. So it's like a proof of TT star like the deformation that connects the physical theory to the TT star geometry. And there's an analogous thing in 3 dimensions. And then the supercharge that's preserved close to the tip of the cigar is this 8-way supercharge, whereas the one that's preserved at the equator is what I called Q earlier.
I mean, at the equator, you can preserve anything because it's infinitely far away, if it's infinitely far away.
Well, if it's infinitely far away, but here it's a finite really thing. I mean, I can stretch it as long as I like, and then, but here the point is that there's also a finite version of it. And then you can think of it in, so you this
Actually, I mean, your Q is just A plus A dagger, QA plus QA dagger, right? So
yes.
those on the isn't it automatically preserved? So in other words, the cigar can be any distance you want, any because of that, because Q is just QA plus QA dagger.
Well, not quite. There is a certain so there's a pi over 2 rotation that I didn't explain. So there are two notions of dagger. One, when you think of this boundary as a space-like boundary and the time is running in the other direction, and one when you think of it as a time-like boundary, and one when you think about it as a space-like boundary. So
I see. So out of the 4 supercharges, we are preserving 2, and you have to. But if it's not the same 2, then the cigar has to be infinite. There's nothing you can do about it. I don't think
that's
so,
right.
Right.
Yeah. So if you really work with the A twist, then you need to take an infinite cigar. But here there's no twist, so it's like a physical background. So the cigar prepares you a state C, and let's say that you are in the Higgs phase, and then you can put this interface here that changes the parameters. And
wait, you have no twist at all?
No twist at all.
But then your fermion's anti-periodic around the cigar, so around the circle. So,
well, they become periodic as you stretch the cigar.
Right, but for the finite cigar.
For the finite cigar, they realize you the spectral flow, so the periodicity changes.
And maybe keep going so we can see where you're going.
Yeah, here's just the point is that you can put these interfaces that change the parameters, and then one can also argue using. So just,
where are you putting the interfaces? The interfaces from this perspective, where?
Well, as is shown on the picture. So I want to change parameters as I move along the cigar.
Oh, good. Yes, and along the cigar. Yes, yeah, that makes sense. Sure.
And then one can actually show by a similar analysis to what I sketched before, where you can change profile of masses, that you can just remove these interfaces, like move them to the left and take them off the tip, and just get whatever you have on the right, just extend it to the entire cigar. And end up with these parameters. Or in terms of equation, it can be written as you take the state in the with parameters and as in the Higgs phase, act with this J and J tilde, and you get state as in the Coulomb phase.
And your cigar is infinitely long, correct? Just to make sure I'm following.
I do, yes, I do extend it to.
Yeah, no, that makes, and so this stuff is happening near infinity. Far out. Yeah.
And now, but so Janus interface, so these two Janus interfaces, they realize a phase transition that transports the state into the Coulomb phase. So it sort of gives you like a vertex function that counts quasi-maps into the Coulomb branch. And of course, if Coulomb branch is a Higgs branch of the 3D mirror theory, and if the mirror admits a quiver description, then this Higgs branch is just a GIT quotient for the corresponding mirror theory. And then there is a clear notion of, like a known notion of quasi-maps. And we arrive at the fact from Aganagic-Okounkov that that elliptic stable envelope gives you a transition matrix that relates vertex functions of the Higgs and Coulomb of your original theory and the mirror theory. But in principle, you can imagine that you don't know.
Wait. This was a little bit fast. Can you do a little bit slower?
Oh, so what I was saying is that this object that I was looking at, that's the this state captures the vertex function in the original theory, right? The quasi-map count into the Higgs branch of the original theory. But now, after acting with these interfaces, I get another object which corresponds to the Coulomb branch. And if the theory has a known 3D mirror description by another quiver theory, then this is, of course, the Higgs branch of the quiver theory. And again, we get the vertex function of this mirror Higgs branch. And because it is described as a GIT quotient, there is a known notion of quasi-maps into that Higgs branch. Right, where you just allow to the map to map to a non-stable, unstable locus at a finite number of points.
Can you say more about what these Hilbert spaces are? Like, you're even setting aside the interfaces, your theory is not time translation invariant in any sense because you've capped off the left side of the diagram. So yeah, in what theory how are you defining these Hilbert spaces? They're like in the previous section, they were the Hilberts, you were talking about Hilbert spaces of your theory compactified on an elliptic curve.
Yes.
What
still the same.
The elliptic curve here, I mean, I see one circle and then I see a time dependent circle, which is the circle part of your cigar.
Yes.
But the, your circle is changing.
Sure. That's not a problem. First of all, of course, I consider the case when this thing asymptotically stabilizes and you just get elliptic curve times r at infinity. So your cigar is like
It's just a cylinder.
a cylinder far away. Yeah. Even if it wasn't, then there's just like a general perspective that you have a boundary of your manifold. And there must be a Hilbert space associated to that boundary. But I'm not claiming to know how. Like, okay, of course it depends on like a germ of your boundary. So like precisely how it is attached to your manifold. I'm not claiming to provide construction in that case. Yeah. So it is really asymptotically a cylinder.
Okay.
Okay. All right. We're good. Then I'll continue. So I was explaining that if the theory admits a mirror description by some known Lagrangian gauge theory, some quiver gauge theory, then of course the Coulomb branch is the Higgs branch of the dual theory, and it admits description as a GIT quotient. And then there's a notion of quasi-maps. And then we can identify this object here with the vertex function that counts quasi-maps into the Higgs branch in the dual description. And so this is kind of like this somewhat heuristic way to arrive at the fact from the paper on stable envelope, on elliptic stable envelopes, that they provide, that they give you a transition matrix, this what they call the pole subtraction matrix, that relates the vertex function of the Higgs branch of the original and the dual theories. But more generally, you can imagine that this Coulomb branch might not admit a GIT description. Like you basically, or you don't know this the mirror quiver theory that would lead to this GIT description. Yet our this physical picture with phases should still hold. So then one could ask, what does this mean? Like it should, in some sense, mean the counting quasi-maps into the Coulomb branch. But as far as I know, there's no such definition known. So it's like I would leave it as a question: how to define quasi-maps into the Coulomb branch.
That's a technical question, right? It's a
I mean,
question
when
of how do you...
when it's not a quiver variety, right? So in those examples, when it's not a quiver variety.
It's a question of how to define a suitable compactification of moduli spaces, not the one that's provided by gauge theory, but by something else. But okay. But it certainly has to exist because I mean, the physical object exists, so there's got to be something there.
Yes, right. But what I mean is that when we describe the manifold as a Higgs branch, then of course there are vortices, and the question is how to count those vortices. They may appear as singularities on the Higgs branch, but let's say you have a description of the Coulomb branch, the BFN definition of the Coulomb branch. Like, how do you? Is there like some geometric definition of?
Well, actually, right. Mathematicians started by just counting holomorphic maps because it's the A model, right? And then they also realized, well, there's a nice, actually quite recently, right? That there's a nice other compactification, which is the stable map compactification. I mean, you can just do it purely in any linear sigma model. So I think the issue with Coulomb branches generally is that they're very, very singular. So that they have bad singularities, nevertheless, the object should somehow make sense. And so to define, I think as long as they're smooth, it's probably not that difficult. You can, model something on counting homomorphic curves. But if they're not, then what do you do? So.
Right. Okay. Thanks. So now let me say a few more words to relation to cohomology theories. So I want. So recall, as I said earlier, that the Q cohomology acting on the Hilbert space is identified as the space of SUSY ground states. And in the one-dimensional case, when we are really in 1D, then it's known that this is just the cohomology or an equivariant cohomology of your Higgs branch, just the classic paper on supersymmetry and Morse theory, where Q and Q dagger are identified with D and D star, or the equivariant versions thereof. And then the Q cohomology is the equivariant Ram. In 2D, is supposed to live to K theory, and it's natural to think of the 2D theory, well, let's say that it's a NLSM into the Higgs branch, a low energy description. If this is 2D theory in S1 cross R, then it's the same as a 1D theory into the loop space. And Q squares to loop rotation. So when we look at this equivariant cohomology, which is also equivariant with respect to loop rotations, and that somehow connects to K theory. And when you live to 3D, there's a similar story, but now you're also equivariant with respect to one more loop. But instead of trying to make sense of this, because there are different literature and points of view on this, instead of that, I'll take the point of view perspective as in Aganagic-Okounkov. Namely, we'll think of this as a scheme over this space of equivariant parameters, which are just flat connections for your flavors on the elliptic curve. So elliptic equivariant parameters. And if for generic equivariant parameters, there are only isolated fixed points, then we can think of this scheme as a classical description of massive vacua. So what I mean, so we have these equivariant parameters. Let's separate them as X and H bar. X corresponds to N equals 4 flavor symmetry, and H bar is this additional one. And then there are also the similar parameters for gauge symmetry or turn roots, which are also flat connections on the elliptic curve, but for the maximal torus of the gauge group. And then in each massive vacuum, the gauge parameter adjusts itself to the value which screens some of these equivariant parameters and allows the matter of F. So that's just how it works out classically. And so classically, you have this picture of like a classical spectral manifold where this is the base, which is the space of equivariant parameters. Then there are turn roots. And then there are certain curves where each connected component in this graph, each irreducible component corresponds to a massive vacuum, and they together they form the scheme LT of X. For example, if you're in SQDM, where the Higgs branch is the cotangent of CPN minus 1, you just have this equation. Well, this is really the spec of the K theory, and then elliptic version is obtained by taking quotient all variables mod Q. So this is just like n copies of CP1, and they like meet at certain points. Now, for a fixed value of these equivariant parameters, massive vacuum adjusts these points that sit above it. and then you get this picture as you vary parameters. But that's a classical description. In quantum case, vacuum, of course, states, so the elements of vector space. So what one should do in this picture is just think that these points that sit on top of the parameter correspond to one-dimensional vector spaces, like 1, 2, 3, so on. The quantum vacuum, isolated massive vacuum, and together they add up to a fiber over a certain vector bundle over this base. Now here I also slightly extended the base, replaced the space of covariant parameters by this product, and also multiplied LT of x by the same thing. So this is the space of Keller parameters, Z. They're also flat connections, but for the topological symmetry, and they must be included in quantum case. And in fact, it's better to think of this as a line bundle on this space, and then the bundle of vacuum is a push forward of this line bundle with respect to this map. So here it's like there's a line bundle over each of the irreducible components, and then they together add up to a vector bundle of vacuum. And don't try to ask me what happens when they intersect.
So these are like background masses or background Fi parameters that are allowed to vary on E tau?
So these are background gauge fields. So there are flat connections on your E tau.
Yeah, are they associated to the flavor symmetry?
Yes.
Or okay, so they're the upgrades of mass parameters, but like if you just took the constant part, those would just be normal mass parameters.
Well,
is that right?
Well, there are mass parameters, and there are these things, equivariant parameters. The mass parameters, so you can so first of all, I never turn on complex masses, as I mentioned a long time ago, because you want H bar to be preserved. Then there are real masses.
Yeah. So
and then there are these things.
And the zero modes of these things are not the real masses?
No. So just imagine having a flat connection on the elliptic curve. So you turn on background flat connection for your flavor symmetry.
Yeah, so if I had like a flat connection on a trivial bundle, that seems like that would look a lot like a mass parameter.
It well, if you it looks like, but it's not a mass parameter. If you reduce, for example, on the circle, then it will become a true mass parameter in the lower dimensional theory.
How is that different from saying the zero mode is a mass parameter? Okay, anyways,
well, let me think how to say it best.
I don't think it's any different.
Okay.
So I mean,
well,
yeah, because everything is complexified, right? You really don't have to worry about intersections because they're in complex codimension 1, not in real. So you can always avoid it.
Right. Yeah, they are in complex codimension 1. That's right. Well, normally when you have masses in theory, they don't appear in your covariant derivatives. So when you do parallel transport, they don't affect anything. But black-brown flat connections, they appear in covariant derivatives. So.
But in your effective quantum mechanics on the line, they all that are
for effective quantum mechanics, they are, of course, they look just like masses. That's true.
And those masses are complex, right?
Yes. And in fact, when you are looking at the one-dimensional case, when you're working with cohomology, then indeed you just have masses. You just have complex masses, which are equivariant parameters. But in 3D, yeah, they are background connections. Now, the topology of this bundle can be determined by 't Hooft anomalies in quantum field theory. Namely, imagine that you put your theory on a half cylinder. So it's our E tau times R plus. At infinity, you fix the isolated vacuum number alpha. And then you want to read off the wave functional corresponding to alpha here at the boundary. Now, of course, so what does it mean? First of all, the Hilbert space that's associated to E tau, it's just given to us. It depends on certain choices, in particular, the choice of polarization on the phase space of your theory. So in this case, phase space is some infinite dimensional space. It's roughly like cotangent space to the space of maps from the elliptic curve into XH, plus some other stuff. And you gotta pick polarization on the infinite dimensional space to, say, canonically quantize your theory. But if we want to pick a supersymmetric polarization that preserves 2,2 SUSY or 0,2 in the presence of H bar, and it turns out that such supersymmetric polarization on the phase space comes from a polarization on XH thought of as a holomorphic symplectic manifold. Or really, because we're in the gauge theory, then we think of polarization or choice of some Lagrangian foliation on this representation space. And so that's the choice of polarization that enters always enters the construction of stable envelopes. And now with this choice of polarization, you can pick, like you would like to evaluate your wave functional on certain boundary condition. And in particular, you could pick some supersymmetric boundary conditions that, like the Dirichlet boundary conditions that fix you your connections, flat connections, flavor and gauge flat connections at the boundary. And what you get will be a certain expression that characterizes your vacuum and how it depends on those connections. Now, I won't be able to give you precise, complete answer because it's that this part clarifying this is really work in progress. But what you get doing this is that these L has sections of the form that looks something like this. And of course, they're expected to agree with the bundle that appears in the constructions of elliptic stable envelopes, like where you have because they are constructed as maps between sections of certain bundles. But it will probably differ by some normalization factors. Now, another thing that I will just sketch is that there must be a sort of effective two-dimensional description. Namely, consider this Janus where mass changes from 0 on the left to really large, and basically you take mass to infinity within a chosen chamber on the right.
Sorry, can you slow down a little bit? So how do you plan to compute this? I mean, what's just go back.
This?
Yeah. So which question from this perspective is the stable envelope an answer to?
No, sorry. So this here it was just the question of the bundle of vacua, not so here not and here just by writing the polynomial of polynomial of a 't Hooft anomalies at the boundary, you can decode how your wave function behaves under large gauge transformations, where you basically shift x by q or s by q. And using a two anomalous, you can decode that, and using that information, just conclude that the vacuum, that the bundle, just conclude that what's the topology of this bundle.
I see. You want to say it's a section of some bundle, but you don't think you should be able to get a direct. I mean, the interesting thing is to try to get a direct computation from physics.
Right. And for that, that's what I'm getting to here in effective 2D description, because what you can do is in this setting where you have, say, sorry. So should I wait, because I felt like I was answering her question?
Yeah, I'm not sure. She disappeared. Maybe the connection.
Yeah. Okay, I'll repeat if she comes back. So so in this setting where you have mass 0 on the left and some large mass on the right within a chosen chamber, as I proposed earlier, this realizes the stable envelope as the map of between these sections of the bundle of vacua. But because the connection goes through the argument, well, okay, this map is determined by the BBS equations, which are gradient flow equations, and since the mass is really large on the right, this gradient flow really happens really fast, and so you don't really need infinite time. Like normally with a finite mass, it takes you infinite time to go from one critical point to another. So it's enough to consider an interval. So it's sort of an effective description where you have elliptic curve times an interval, and on the left, mass is 0. On the right, mass is infinite. And the partition function on the interval, it's like this question of interval reduction, will lead to a certain effective 2D n equals 0,2 description on the elliptic, like effective 2D 0,2 theory on the elliptic curve, whose elliptic genus computes you matrix elements of STAP. So you fix boundary conditions that correspond, that are equivalent to having vacuum at infinity. And then such computation leads to formulas for stable envelopes. And it actually works in some simple cases, but in general, one expects to write pretty general formulas, like for given representation content of your theory. And this part is really also in progress. So there was just this sketch. And finally, this also leads to our matrices, where, so that's the construction from Maulik and Okounkov, where you take the two stable envelopes, STAB and STAB inverse, and compose them. In this language, this is realized via this Janus interface, where you have mass in one chamber on the left and another chamber on the right. And we think of them as being very large. For example, in the 1D QFT case, we get a map between the equivariant cohomologies of the fixed loci. And then, but this is some non-trivial map because that's like this wall crossing happening as you go from one chamber to another. And the interface supports some trapped modes. For example, it's like a well-known fact for when you have a Dirac fermion with this mass profile where the sign of the mass changes for like a step function. Then at the boundary between the two regions, there's a chiral fermion trapped there.
So sorry, Mykola. My computer died. So I lost like 5 minutes. Can you just flash just go a little bit up so I see what?
Yes.
Can you just briefly summarize what you're saying here?
Yes. I guess that you probably so so the idea is that you have this setup. Oh, sorry. There's this setup with mass 0 on the left and really large mass on the right, and which supposedly realizes stable envelope. And because BPS equations are, as I said before, the gradient flow equations, the gradient flow, it really, with a finite mass, it really takes infinite time to get from one vacuum to another. But if you take mass to infinity, then you can imagine approximately that it's like you stay in one vacuum and then you just jump to another vacuum. It takes you finite time in this limit to get from one vacuum to another. So the proposal is that there is this effective description. Once you take mass to infinity, you don't really need to have infinite line, and you instead can consider an interval. So the setup is here that you consider your theory on the interval, where the mass is 0 on the left, and the mass is this infinite on the right. And at the boundaries of the interval, you fix boundary conditions that correspond to choices of vacua. And then the partition function on this setup, on this geometry, it's like a partition function elliptic curve times an interval. It leads to interval, then like the idea of interval reduction, and that there's a certain effective description as by 2d 0,2 degrees of freedom on E tau, and then the elliptic genus gives you the matrix element of the stable envelope. So the idea basically is that such 2d 0,2 computations on E times an interval, they can give you matrix elements of step. And it basically works in like T-star CPN or in T-star Grassmannian examples, but there's still some details that should be clarified. But
I think the key question is, can you compute the Hilbert scheme of points on C2 this way?
I don't see any immediate obstructions to doing that. So, yeah, it should be possible.
I mean, for theories which are basically abelian or easily abelianized, it's not difficult to do this. But for the Hilbert scheme, things become interesting at 4 points. Hilbert scheme of 4 points.
Mm-hmm. Yeah, so yeah, I haven't looked at such quivers with loops yet, so I cannot tell much more. But the general construction seems to suggest that it should be possible. But and then I was saying that
this is actually how we originally computed as elliptic genera of sort of effective theories on the Hilbert. Well, I haven't tried, again, with some knowledge of papers of Smirnov or so forth, but back at the time, I could not compute a Hilbert scheme of 4 points. There was just no way to do it. Not for me. So
I see. Well, okay, it's we'll look into that. Good to know that there's some interest.
Basically, it's for simple enough theories, it's easy enough to see what is the effective theory on the once you shrink the interval. But like for the Hilbert scheme, for example, I could not figure that out. So. And yet there should be a way to do it for sure. And that's a solvable problem. So it's a really good one.
I see. So is that how you thought about it too, in terms of interval, or
we computed it from physics first. It's just.
I see.
Mina, is it right that is it Smirnov has a paper computing the elliptic stable envelope for the Hilbert scheme of points mathematically?
Yeah, he does.
That's right, right?
It's fairly recent as far as right.
You got some construction of Simon over trees, right? Of the Young diagram.
Right, with some paths in some Young tableaus.
Yeah, I think the cases where fixed points are isolated, even in absence of H-bar deformation, and when they're not, are very different. So if the fixed point is essentially isolated even without turning on H-bar, then it's not difficult. But if they're not isolated, then one needs something new. And so.
That happens when we have, say, two loops, right? So not one loop, but say more. Right? It's a Hilbert scheme.
Yeah, two loops. That's right. You always have one loop in these theories, but yeah.
That's right. Yeah.
Well, yeah, then the only remaining thing I wanted just to mention is that the R matrices in this language are also Janus interfaces where the mass just goes from one chamber to another chamber. And the boundary in this case might support some additional trapped 2D degrees of freedom, and so computing partition functions again in this case would lead to matrix elements of the R matrices, and such interfaces can effectively change the rank of the gauge group by Higgsing. As an example, consider this theory that realizes you T-star Grassmannian with rank of the gauge group n+1 and l+1 flavors. Then and then there's this U1 symmetry that rotates just the last n+1st hypermultiplet. Then the fixed locus has these two components that just Grassmannian of the T-star Grassmannian of n and n+1 dimensional planes in CL. At the QFT level, the mass breaks theory into subsectors. Namely, if you turn on this mass and make it really large, and you really get the direct sum. This is one of those rare cases where you get the direct sum of theories, a sector that is like this, and a sector that's like this, and then this leads to a 2x2 block matrix where the blocks either talk within the sectors, or talk between the two sectors. And okay, again, this just a sketch. hopefully more concrete things, and particularly about the computation of these matrix elements as elliptic genera, would be in the upcoming paper or papers. And that will be it. That's all I wanted to say.
Thank you.
Thank you.
No
Any more
questions?
questions?
So in this whole talk, you've been transitioning between different parameter values for the same theory. But could one, it doesn't seem essential that it is the same theory. Could one imagine studying matrices relating vacua of different quantum field theories?
Yes, definitely. So you can sort of just give an a priori construction of like some interface that connects you to theories. You can have one theory A here, theory B here, and then there's some boundary conditions matter at the interface. But here also the point was that there's a natural way to start, like to get this within one theory. And in particular, that's what the last thing that I was mentioning was that you can start with this one theory, and then by using this particular mass, you can break it into subsectors and then effectively get interfaces between these subsectors that look like interfaces between different theories.
So you lose the naturality if you're studying interfaces between different theories? Is that the concern?
It's like, well, I'm not sure if that's the, yeah, sort of like you have a lot of freedom. Like you can, there's a lot of freedom in constructing such interfaces. You can put any matter at the boundary. Just make sure if you have some gauging, make sure that anomalies are canceled. Eventually, they would lead to some linear operators, of course, between the SUSY vacua and if there's only finite number of vacua, then of course there's going to be some finite dimensional matrices. I guess that's it's probably interesting to, I don't know how interesting it is. So somewhat interesting to. Well, I'm sorry, it's actually straightforward to identify matrix element of that matrix. It's just going to be the computation again of 2D elliptic genera for this matter at the interface. Again, you cut the interval, like you cut on the left, on the right, compute matrix elements. Yeah, so yes, that's something that can be done.
I mean, people do this. I think that the first thing is to get used to thinking about boundary conditions in a single theory as interfaces between a trivial theory and a theory of interest. And since boundary conditions, in some sense, are always a choice of Lagrangian in field space, that's not so weird. And in fact, I mean, symplectic geometers have learned to think about things that way. So basically, we already know how to think about quantum mechanics that way. So then you can, yes. It's probably just a question of just getting used to the language. It's not even that exotic, as long as your theory is. Yeah.
Mm-hmm.
Yeah. Yeah, but understanding what is the categorical version of this, I think would be really interesting. And you're almost there, I think. Once,
okay.
As long as you have a three-dimensional theory on a circle, right? It's a cousin of theories. Basically, your whole story is an uplift of constructions we know very well in one dimension lower. In other words, in 2 dimensions to 3. Yet in 3 dimensions, there are some interesting things that do happen that.
So, okay. So I replace one of the circles by a line. I guess fix some conditions at infinity. I want and the two both.
Yeah,
infinity.
and in fact, there's this interface. I mean, you can think of it as defining like a symbol, like boundary condition. And yeah, so in fact, one computation of the stable envelopes would be, I think, just this intersection between this.
I see. So I guess the upgrade. So okay. So in this in the computations that I was talking about, when you look at the matrix element of the stable envelope, that's like an index. So I guess when you do this upgrade, you should get instead some vector space or.
Yeah, I mean, you're just getting the space of supersymmetric ground states on the interval.
Right. Oh, right. Ah, well, yeah. Well, okay. So that's yeah. Almost immediate. Yeah.
Right.
Yeah, but these questions of ground states and the interval, they're actually surprisingly delicate. Like it's very easy to break SUSY. It's like you need to take special care to actually make sure that there are ground states. I think.
No, I think the fact that you preserve, as long as you think of it as supersymmetric quantum mechanics on the interval, a theory is very flexible. In particular, this is why you can, allow variations with y as you like, and preserve supersymmetry. As a supersymmetric quantum mechanics on an infinite dimensional target space.
But what I mean is that, let's say I fix values of the gauge fields at one, like say from flat connection on this boundary and flat connection on the other boundary. And the BPS equations tell me that everything localizes on flat connections everywhere. So if these two are different, there would be no solution. And that suggests that the answer is just 0. And so that there's no, in this sector, there's no like SUSY ground state.
Which I didn't quite follow what you did, but that might be an answer. It happens often. Yeah. I'm not sure that's the right answer here, but
yeah, I guess that's fine. Yeah, just
So your perspective here is to formulate everything in the short distance theory, in the gauge theory, or in the at long distances.
In the gauge theory, yeah. So in particular, so there's this thing that here, when we have chambers or walls, they are really just planes, right? But when, for example, so there's this somewhat puzzling feature. When, for example, you look into paper on holomorphic blocks, they have some non-trivial, highly non-trivial walls. And I think that that's the effect of the sort of UV-IR map, that in the UV language, in terms of this bare parameters, you have just flat walls where the matter multiplies become massless, while in terms of the IR parameters, you get some non-trivial walls.
Which paper on holomorphic blocks? I mean, which story?
Like the BM Dimov Paschetti, the
what are they going to tell you that you didn't know here? I mean, in fact, well, so I don't think so. I mean, in some sense, the theories they studied, they thought of them extremely flexible. You know, you can put any supply of any boundary theory, any theory in the boundary makes sense. And so this story in fact started as sort of noticing that there's rigidity to the story, that if you pick a nice set of boundary conditions, then wonderful things happen. Like, you know, the theory just solves analytic continuation problems and so forth. So I don't think you should worry about those things. I'm not sure which part of that paper you're referring to, but
well, I'm just saying that when they determine walls in the space of parameters, in the space of mass parameter, complexified mass parameters, they have some non-trivial structure. Like they are not flat, like not just planes. But of course, those are walls in the dependence of the holomorphic blocks on those parameters. But well, this UV description suggests that the walls are just
I think that's good. Sure, yeah, absolutely. So, I mean, do you again? Do you envision that eventually one will be able to say, okay, well, this is the theory that that lives on the interval, right? As on supersymmetric H theory, or as just a computation that I guess I had already asked you this in some low energy effective theory, where you know we can
Sorry, I'm not getting the question. Can you say again?
If one is lucky, one should be able to formulate one should be able to understand which gauge theory lives on the wall.
On the wall, okay.
Yeah.
Mm-hmm.
Sort of the way Guyot and Witten were lucky. That's one way one could get lucky. But my impression was that for the Hilbert scheme, you might actually have to have an answer of that kind. That you know, they studied these Janus interfaces in 4 dimensions, and then of course a posteriori there was a reformulation of a theory we already knew, but that this wants to have such, you know, such kind of formulation just in this more general problem, and that should actually exist.
Yeah. Yeah, I definitely believe, at least hope that this will. Yeah. It looks like in every problem with you can't just quantify what are the fields on the wall.
Yeah, I mean, I think with just the right angle, these problems are definitely solvable. They're
Mm-hmm.
Yeah, this should be very nice. It's not going to be something where, you know, we'll never know an answer to. We'll know an answer to. One just has to get a just right angle at it. Okay, any more questions, comments? Okay, let's then thank Mykola again. Thanks for joining us.
Thank you.
Thanks a lot.
All right. Bye-bye.
It was a very stimulating discussion. Thank you.
It was a lot of fun. Thanks for coming.